So in this video I'm going to show you some of the conventions of ways that heat is incorporated into a chemical reaction. So I'm going to go back to the lab that we just did where we calculated the heat of fusion of ice. One way, well, let's see, I don't want to do that. Let me get rid of that. The reaction that you did was you took H2O solid or ice and you converted it into H2O liquid. Now the heat that required, you calculated out, and we messed around with it, and it turned out to be 6.01 kilojoules per mole. Now there are two ways I can incorporate this amount right here into the balanced equation. The first way is that was a positive amount, okay? And because it was positive, that is said to be endothermic. It also means that it would be incorporated into the reactant side of the equation. So I could write the melting of ice to look like this: 601 kilojoules, and then that's going to go to H2O liquid. So that's one way that energy is incorporated into a balanced equation. The other way, which is probably a little bit more common, is I go back to my reaction, it's a phase change, going to H2O liquid, but this time I set out of the equation the enthalpy, delta H equal to a positive 6.01 kilojoules per mole. Alright? Now, normally in thermodynamic equations or thermochemistry equations, things are written per mole. So, in this case, it takes 6.01 kilojoules to melt a mole of ice. Alright? And these two, this is saying exactly the same thing. Because I have incorporated the 6.01 onto the reactant side, it implies the same thing as a positive enthalpy change, both being endothermic. Alright? So, that's one part to this whole thing. Now, I'm going to go to another page. I want to show you. Alright? So, going back to what you had. H2O solid going to H2O liquid, the amount of energy that took was 6.01 kilojoules per mole. Alright, so I got that. Now if I flip this reaction, if I just reverse it, okay, writing H2O liquid going to H2O solid, what I find is delta H, the enthalpy change, is still the same magnitude, 6.01 kilojoules per mole. But what has changed is the sign. Now it becomes negative. So that negative means that this was an exothermic reaction or process. Okay, and I could have incorporated it into the whole reaction this way. H2O liquid goes to H2O solid plus 6.01 kilojoules per mole. Just like in the other example, these mean exactly the same thing. Two ways doing the same thing. Alright? And it drives home this idea of the sign on the enthalpy change. When it's negative, as in this case, when you get that negative sign right there, it means it's going to be exothermic. It also means that it can be added to the product side of a reaction. Now I want to show you what we do with those. Okay. So, going back to what I had H2O. I'm going to go back to what the lab was. Solid going to H2O liquid. The enthalpy change for that was a positive 6.01 kilojoules per mole. Now let's say you have a problem, and the problem asks something like this: how much energy is needed to melt 250 grams of ice? Alright? So what you would do, okay, what you would do is, if you didn't know it, you would look up what the enthalpy change for melting ice is. And another word for that, in this case, would be heat of fusion. Okay, so I got the heat of fusion sitting there. So now, all I need to do is convert those 250 grams into moles. So the way I would do that would, I'd say 250 grams times 1 mole of water weighs 18 grams times the fact that I have 6.01 kilojoules of energy required to melt every 1 mole of ice. So I set that up. It's going to be 250 times 6.01 divided by 18, and it tells me that I would need 83.5 kilojoules of heat to melt 250 grams of ice. Okay?